Okay, so are there any other questions? Okay, now the test is already, it's been done. I did it on last week, but it's not available to you till Wednesday morning at 12:01 a.m. And you'll have till Saturday, and you have a full 2 hours to do that. So so make sure you try it out. So if there are any technical difficulties, we can fix those by the time Saturday midnight rolls around. Okay. Is your kitty adding the cognitive insights to this lecture?
Yes, she enriches my intellectual endeavors quite often.
Yes, I just found out 20 minutes ago, my daughter has a new puppy. She has a new golden retriever. That makes 2 golden retrievers plus a Yorkie in her house. So she's got quite a plus 2 children, and pretty cool though, actually. Okay, all right, so let's jump over to our OneNote. Now, one of the things I mentioned last week on Friday was that the yellow highlighted part of that periodic table, I want you to really practice the elements within that first 3 periods there, period 1, 2, and 3, in terms of writing electronic configuration, like for phosphorus versus nitrogen and all this stuff, okay? Now, the other thing we reviewed was the reason that groups have similar chemistry in terms of the valence electron configurations are the same within those elements that are in that group. In other words, phosphorus and nitrogen have the same valence structure, hence their chemistry is the same. Oxygen and silicone, another example. Fluorine and chlorine, all those are examples of elements within the same group having the same valence configuration, valence electron configuration, hence their chemistry is the same. That's crucial, okay? And I can't emphasize that enough, okay? So hint, hint, hint. All right, okay. Now, one of the things that we've looked at this periodic table here, and it's kind of goofy the way these F block electron elements are down here. Well, the reason they're down there is because the original periodic table looked like this. And this was very awkward in terms of publishing environments. Literally, publishers forced us to look at the periodic table like this, not because this is the most logical, because this is the most logical periodic table. Okay, this guy here. And you've probably never seen a periodic table that looks like that, but that's really what it looks like. So what happens is, what they've done from a publishing standpoint is they've taken these guys and moved them down to here. Because a lot of the chemistry kind of discussions focus around the upper one, not the ones down here. So it works. It's just I want to make sure you understand that this is really what it looks like, these two. And then we can add, since this is an older version here, really those are 7p electrons over here. Those are all the newly discovered ones within the last 5 to 6 years. Okay, so are there any questions about any of the electron configurations for the first 3 periods? Hopefully, some of you have gone back and actually practiced some of these. For example, let's do a quickie here. Let's do oxygen. Okay, oxygen is going to be located This is going to be carbon, nitrogen, oxygen, fluorine. So oxygen is 1, 2, 3, 4 into the P's. So to write out oxygen, we have to consider we have core electrons, which are going to be below that, which is the 1s2. These would be core. Then we have 2s2, 2p. How far in are we? 1, 2, 3, 4. So it's going to be 2p4. That's core, because it's down 1 from the highest one. And that would be valence. And remember, core electrons are super, super, super stable. So they don't participate in any chemistry at all because of the stability nature of them. But the valence electrons are not particularly stable. So they're going to highly influence the chemistry of oxygen. Now, a couple review here. We have 4 electrons in the P subshell. This would be shell 2. It's like this is shell 2. Now, oxygen has how many electrons? You look at the superscripts, 2, 2, 4. That means that you have a total of 8 electrons. And these electrons total. Excuse me, how many valence electrons? Okay, those are going to be all in the 2 shell. We have 1, 2, 3, 4, 5, 6. Okay, verify that. 2 and 4, 6 valence electrons. 2 cores makes that a total of 8 electrons. Now, are we all okay on doing the valence or the electronic configuration for oxygen? Another way you may have seen it written would be like this. And what they do is they represent the core with a noble gas. And since the core doesn't do any chemistry, they want to abbreviate it and not complicate things. They want to focus on the valence electrons because that's where the chemistry is. Yeah. Okay, so any questions about doing the electronic configurations for those first 3 periods up here? Because it's going to get slightly different when we get down to period 4. Okay, now let's go ahead and look at period 4. Notice period 4 starts off with 4s, just like up above. However, notice the gray Ds are not 4 level, they're 3 level. And then over here, it jumps back up to 4 level Ps. Okay, so it goes 4 to 3 to 4. Shell 5 would be 5, 4, 5. And we're going to look at over here now. So we're going shell 4 goes 4s, 3d, 4p, 5s, 4d, 5p. So, excuse me. So the p's and the s's are always at the same level. The d's and the f's are not. Notice shell 6. We have the f's introduced, and the f's are 4, it should be 2 levels down from the 6. So it goes 6s, 4f, 5d, 6p. 7s, 2 down, 5f, 1 down, 6d, 7p. Okay. All right, so what would that look like? Let's choose now a element. Let's look at iron. Okay. Now iron is 1, 2, 3, 4, 5, 6 in. So 1, 2, 3, 4, 5, 6. So iron is going to be right here. So how would we write that configuration? Now notice iron is in the D's. And D's are 1 down from the S. Now, one way to remember that I teach my students is the D's are dumb. They're dumber than the S's. So they're 1 down. And of course, the F's are even further down. They're 2 down. Okay, so D's are 1 down, F's are 2 down from the S's. Okay, so let's look at iron now. Remember, iron again is 1, 2, 3, 4, 5, 6 into the D's. It has 26 electrons total, but not all of them are valence. We have a whole bunch of core electrons. Now I'm going to write this out 2 ways. One abbreviated form using the noble gas, and also I'm going to write it out long ways. Now notice iron is here. That means, like I was doing Friday, we're going through, and I'm going to just kind of make a travel trip through the periodic table. And as I go through getting to iron, I'm going to write down the electrons and the blocks they're in. So we're going to go 1s1, 1s2, 2s2, 2p6, 3s2, 3p6, and then lastly 4s2, which are the valence electrons now. And we're 6 into the D, so that's going to be 3d6. Okay, notice 4, that means these guys are core. Valence. Okay, so we can represent the core by looking at a noble gas that has the same configuration as 1s2, 2s2, 2p6, 3s2, 3p6, which is 1 up noble gas, argon. The other way to do this is to go like this: argon, 3s2, 3p6. Excuse me. 3d6. Those are in the D's, not the P's. Okay. Excuse me. Okay, so this here is here. This is represented by argon. Okay, so to do the noble gas shorthand, you go up a row over to the right. And that's the noble gases, and that will represent all the core electrons. Okay, up a row to the right, noble gas. Just like here. With oxygen, you do the same thing. Up a row, here's oxygen. Up a row to the right, helium. So we could go. So that would be the other way to right. Just as short to right, 1s2 with helium, but anyway. Okay. So that's iron. You can see how much simpler it is when we represent the core electrons as a noble gas. Okay. So we're representing a noble gas as a representation of all the core electrons. Because remember, the core electrons are not that important because all they do is they add, because they're so stable, they don't add anything to the chemistry of the element. Only the valence electrons do that. Hence, we just show the valence electrons. Okay, did everyone follow that iron example? Okay, gosh, let's do another one. All right, let's see here. Let's clean all this up. Let's do, oh, I don't know, let's do, manganese. How about molybdenum? Okay, now molybdenum is in shell 5. And real quickly, what's the noble gas? We're going to use it as a shorthand for molybdenum. We go up 1 all the way over, and that is krypton. Okay, so we're going to use krypton. And it's in shell 5. And 4D. And how far is in the D's? 1, 2, 3, 4. Okay, so if we look at it up here, so shell 5, so we have 5s, 4d, 4n, and we're using krypton representing the core electrons.
I have a quick question.
Sure.
How far did you know how to go to kryptons?
Up 1, over to the right.
Over to the right, all the way to the end?
Correct.
Is it always like that?
Always, no exceptions.
Okay.
So it doesn't matter where you are, up a row, all the way to the right, to the end, because you want the noble gas. That's where the noble gases are located, at the very, very end. Okay, so we're having 5s, and how far in the D's were we? We were 4n, so it's going to be 4d. Now, if we wrote out the longhand way, we're going to have to get up to krypton, which is going to be okay, that's krypton. core. And all I did to write that out we need to get here where krypton is. We're going 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Now there are 10 spots in the Ds, 10 spots, and 14 in the Fs. Okay, and then 4p6. That's how I came up with crypto. Okay. Let's do a more complicated one now. Are there any questions so far? That was a good question about how do you know when to put in the noble gas. Up one, all the way to the right. Okay, so let's do one. Let's do uranium. Uranium. It's wildly complicated, but not if you look at it this way. Okay, so here is uranium right here. So how are we going to do that? It's in the Fs. It's in the Fs, and it's 1, 2, 3, 4 into the Fs. It's also in shell 7. Okay. Oh, and then we're going to first do it the shorthand way. So we're going to do it up one all the way over. So it's going to be radium. $92 electrons. So we're saying radium. Okay. And it's at subshell 7, so that's 7s2. Five F. Four. Now let me show you the longhand way of doing that. So we got to get to radium. Yeah, we're out of room here. What does that tell you? That's radium. And then 7s2, 5f4. Those are all core electrons. They don't do anything for chemistry. So why complicate it adding all those in? They do exist though. It's extremely important to understand they exist. So they're there. They just don't participate in the chemistry. So the real chemistry is over here, valence electrons. So we have 4 electrons in the F block. I'm going to talk about what that means in a second more here. And we have 2 electrons in the S block. Okay, so in the second half of the lecture, I'm going to talk about, we're going to subdivide the subshells. I'm going to go back up to simple examples up here. And we're going to talk about, now that's the third level of organization for defining the electrons in an element. First, we had shell. And we have the subshell. Now we're at the orbital. And then there's also something even lower than that, which is called the spin. So what is the orbital? Now, orbitals basically, again, are where electrons occupy because they're super stable areas. And those super stable areas, you can only have 2 electrons per orbital. Remember, some of the subshells have 2, 6, 10, and 14. So if the subshell has 2 electrons possible in it, how many orbitals would that subshell have? So this is the subshell. So if a subshell has 2 in it, this would be the S, P's, P's, and S. So the S's, how many orbitals would be in the subshell S?
1.
1. Basically, you're asking yourself, how many 2s are in 2? 1. Okay. P, how many orbitals?
3.
How many 2s are in 6? 3. How many 2s are in 10? How many 2s are in 14? So this is the number of orbitals that are allowed in subshell S, P, D, and F. Okay. So the spin of an electron has to do with something similar to a magnet. How many poles are in a magnet?
2.
2, north and south, right? Nothing in between. So it's one or the other. Okay. Electrons are similarly have a magnetic component to them, north and south. And we can't have any more than that. It's either one or the other. But we can only have 2 electrons anyway. So one's going to be north, one's going to be south. And we denote that by an up arrow and a down arrow, or a down arrow and an up arrow. Doesn't really matter. The main thing, though, is whenever you have 2 electrons residing in one orbital, they have to be complementary. They have to be north to south. Just like 2 magnets, the easiest thing for 2 magnets coming together is not north to north, because they'll repel. It's north to south, and they attract. So that's more stable for that magnet. Same with electrons. They've got to have opposite spin, or it's called a magnetic angular momentum component. Blah, 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 blah. Bottom line is the spin is the opposite. Okay? Represented by these arrows. So we have 3 orbitals here, and I'm going to make this orbital resonance. And depending on what book you're reading, what text you're reading, what article you're reading, the orbitals are represented with either lines, circles, or boxes. My particular notes represents them with lines. Okay, so if we have 3 orbitals, that means we have 3 lines. We have 5, we have 5 lines. Each one represents an orbital. And then we have 7 as well. So now we're subdividing subshells into orbitals and then spin, electron spin. Okay, so let's now go to an example. Let's look at oxygen again. Oxygen was 1s2, 2s2, 2p4. Okay. All right, so let's look now at the orbital representation of oxygen. Now we're not going to look at the core. The core we're just going to represent as helium. One other thing, of these sets of electrons, which do you think was the most stable of those 3?
The 2s.
Look at the whole thing. If you're looking at valence, yes, it's 2s, but look at the whole thing. What would be the most stable?
The 1s2?
Yeah, core electrons, right? Okay, if we're going to look at an energy diagram, remember the lower the energy, the more stable. We would put the 1s is there. 2s is there. As you mentioned, they're more stable. And then lastly would be the p's. And again, the lower the energy, the more stable. So the lower number shells are more stable than the higher ones. They're also closer to the nucleus. So the electrons can be attracted to the nucleus easier because they're closer, hence they're more stable. That's why we look at the lower ones first when we're writing out a configuration. It's because we're going this way, stability. Okay, so let's look now at the valence electrons. Okay. We already mentioned that the s electrons have 1 orbital. Or you mentioned the p's have 3. Now, how many valence electrons total do we have?
6.
6. That's right. 2 plus 4. Okay. All right. So these guys, now this is at the 2 level. So these 2s are going to be here and here. Notice again, I write the electron's directional moment. A lot of jargon here. Just like the north and south poles of a magnet, got to be opposite. Okay, the P's now have 4 electrons. Now this is the way they're going to be filled. And I want you to notice this now. I'm going to fill each one separately until I run out of orbitals. So I'm going to put one here, here, and here. And I've run out of orbitals to put the 4th one. So what happens now, I'm going to pair up one of them. That. So in other words, it's not going to be like this. Because that is more unstable than putting them individually in all the orbitals first. Now, a couple comments about that. Nature likes symmetry. This is more symmetrical than that. This is very lopsided. Nature does not like that. It's not symmetrical as this one here is. Okay, I want you to keep that in mind. Okay, stability rules the game. Symmetry is one of the ways an atom can achieve stability. It's through the symmetry of the electron layout. Molecules, same thing. The layout of the atoms that make up the molecule. The more symmetrical they are, the more stable they are. Okay. Let's see where we are. And this is what we just did right here. Now, let's do one more, then I'm going to do a noble gas. Okay, so let's continue on with this here. So this is the orbital representation. The orbital representation of the valence electrons. And again, it's not going to be like this. You're going to fill each orbital with 1 electron first. Then when you run out of orbitals to put them, then you're going to start pairing them up. Okay, and okay. Hub's rule is the name of the law we're going to be using to fill each orbital first with 1 electron. It has to do with stability. Okay. The Pauli exclusion principle has to do with, let's see, where are we here? Pauli exclusion principle means that every single element has a unique electronic configuration, truly unique. That's why the chemistry of each element is unique, unless the valence is the same. Because then the Pauli exclusion principle says then that if those are the same, then the chemistry is the same. But when you look at the whole configuration of each element, they're unique. And what makes one unique versus the other, even though the valence electrons have the similar or exactly the same electronic configuration, are the core electrons. So the core gives it the uniqueness. The valence electron configuration gives it its chemistry. Okay, so let's look at sulfur. Sulfur is right underneath oxygen. I'm going to do an orbital representation of sulfur. Okay, first thing I'm going to do is I'm going to write out the electronic configuration. Okay, it's going to be, we're going to do the abbreviated one. So we're going to go, excuse me, up one row all the way to the right. First sulfur. Sulfur's right here. So up one, so it's going to be neon. Okay, and then the valence is going to be 3s2, 3p4. Okay, so let's look at the orbital representation now. So we're going to have S's and P's. S is one set of orbitals, P's are 3. So we have 6 total electrons. We fill the S's first because they're more stable. Remember the diagram I did, the S's are lower energy than the P's. So that means they fill first. Okay, we have 4 electrons in the P's. We're going to go 1, 2, 3, 4. And this is equivalent, by the way, if we went like this. That's the same, okay? Or you can have it over here, either way. I usually fill it left to right, but it doesn't have to be. Okay, so that's sulfur. Now, another thing is just a little comment. This is a pair of electrons, single electron, single electron. So sulfur has 2 pairs, 2 singletons. Oxygen has 2 pairs, 2 singles. Again, that's what makes the chemistry of sulfur and oxygen so incredibly similar, is because they have the same number of paired electrons, the same number of singleton electrons. Okay, hopefully you can start to see a pattern here of why the chemistry is so unique to these groups. Everyone in the group has the same valence configuration, same valence orbital configuration, on and on. hence the chemistry is the same. We okay so far? Okay, now again, we're doing neutral atoms only. Wednesday, we're going to hit upon ions. And remember, ions have either more or less electrons than the neutral atoms. So they're going to be adding into these orbitals in different ways. Okay, let's do a D. Let's do iron again here. Let's go up here to, where's our iron here? Here is iron right here. Okay, so here's iron. And let's look at the orbital representation of iron. Now, as we saw from before, iron has got D electrons. Okay, the maximum number of electrons in the D block are 10, so that means we have 5 orbitals. Okay, so we have 1 for the S, 5 for the D, and we also have some empty orbitals. And those are just kind of placeholders. Those are also stable areas, but we have no electrons are going to fill them. So, but they're still there. Just keep that in mind. Even though there are no electrons in it, there are areas of stability these electrons can go. That's why sometimes these electrons might jump. Okay, so this is iron. We have 2 electrons in the S. We have 6 electrons in the D. So we're going to go 1, 2, 3, 4, 5, 6. So that's what iron looks like.
How do they jump again? Was it energy or explosions or something?
Yeah, exactly. If we put energy in the system, we might take, in fact, this electron here would be the one that would then go over to here.
Got it. Thank you.
And let me add, P's are higher. Remember, we're going to go S, P, D on our energy. So, excuse me. So we promote an electron here up to here. It's making it more unstable. So what does that electron want to do?
Doesn't want to go back?
It wants to go back, yeah. So it takes energy to go up, and then when it comes back down, it gives off energy. And if the energy is in the visible spectrum, we'll see it. If it's not, if it's in the infrared or ultraviolet region, we won't see it unless you're a bee or something like that. The other way to see it is with an instrument that has sensitivity in the infrared and the UV. And those are very common instruments. They're called infrared spectrophotometers, visible UV spectrophotometers, and they will actually not only see the light being given off as it comes back down, they can also then measure the intensity of it as well. And when you get into 400, you'll be using these instruments. When you get into the organic series, you'll be using them like all the time. This is the deal. We put energy in, one of the electrons, and the electrons of these 6 electrons The one that's most unstable is this guy here, because once this leaves, now we have something very symmetrical. We have a subshell that has one electron in each one. That's nice and symmetric. Right now, it's a little lopsided because we have one here that's doubled up. In fact, when we get in on Wednesday, we get into ions, the one that's going to leave is going to be this guy here. So we'll end up forming a ferrous cation. That's for Wednesday. Okay. All right. So anyway, if we were to put energy into the system, it needs a place to go that's stable, relatively stable, but still less stable than the D area. And then when it comes back down, let's see. Energy is given off, put energy in to move it. Okay, but the bottom line here is, this is the orbital configuration for iron. Okay, so you have 6d electrons. We first fill 1 electron per orbital because of Hudd's rule. And then when we run out of orbitals to put single electrons in, we have to start pairing them up. And we pair them up in opposite directions. Okay, so that's the orbital representation of iron. Let's do molybdenum. Okay, so there's molybdenum. Okay, so here are valence. Okay, so we have the S's, we have the D's. Remember, there are P's over here that are empty. We're not gonna have to list them down, but they are there. Remember, orbitals are areas of stability, and there are 3 p orbitals that offer that stability. Okay, so we have
I have a quick question.
yes.
Do you only use for the orbital representation? Do you only use the valence? The valence?
Yes, because it's a waste of time to do the cores because they're going to be all filled up and they don't do anything. So 99% of the time, they only look at the valence.
Oh, okay. Thank
But you
you.
can do the same deal, the orbitals for the core as well. They're just going to be totally full and very stable and all that good stuff. So it's like boring. So we want to focus on the valence because that determines the chemistry of the element. Good question. Okay, so we're looking at 2 S's and 4 D's. I notice we have an empty D orbital there. So let me ask you, which which do you think is more stable? Top or the bottom one?
The bottom,
Why? Yes, that's correct. Why do you think it is?
all the spots are full.
All the spots are full, nice and symmetrical. Okay, so this is not totally full, so it's going to be a little lopsided. Nature likes nice symmetry. Does that make sense? Okay. All right. So what I want you to do between now and Wednesday, it's very important to practice this stuff, because when we get into on Wednesday, we're going to be looking at the ionic versions of all this stuff. In other words, what does iron plus 3 look like? Why do ions even form? And we're going to show why ions form by looking at their electronic configuration versus the non-ionic form. In other words, we're looking at elemental iron versus iron plus 1, iron plus 3, iron plus 2, etc. Okay, so it's important to understand how to do neutral atoms between now and Wednesday. You'll get a lot more out of the lecture if you do that. If you're not live right now and you're listening to a pre-recorded video, before you look at Wednesday's lecture, practice doing neutral atoms first. Now, I've given you lots of extra worksheets regarding this in modules. So besides the worksheet, the official worksheet, I've also given you extra practice, because this requires lots of practice. Unless you're a savant, my hat's off to you if you're a savant, but most of us don't learn that way. Okay? All right, so any last minute questions? Okay.